All right, so we're going to pick up where we left off, which is on lesson 5.2, which is dealing with Newton's laws of motion. So first off, let's just kind of go through the three laws and try to talk about each one individually and how they apply to motion. But what you should know also is that all the laws work at the same time. So it's not like there's only one law happening at a time. These three laws govern all of motion at all times. So you can apply them to every type of motion we study. So the first law is Newton's first law of motion. It's known as the law of inertia. And if you read this caption or this description up here, it says an object that is at rest will remain at rest, and an object that is moving or in motion will continue to move in a straight line at a constant speed if and only if the net force acting on the object is zero. So this is kind of the law that deals with balanced and unbalanced forces, which we've talked about when we first started talking about like net force and how forces like are just pushes and pulls and they work together. So I'm gonna kind of highlight a couple things and break it down into different parts because that's, I think, an easier way to describe it, because if you try to take it all in one big chunk, it's a lot. So the first part here, I'm going to underline. It says an object at rest stays at rest. I'm going to use that. And then I'm going to say if and only if the net force acting on an object is zero. So what that means is if something isn't moving, it's not going to move by itself. So if something isn't moving, if something's at rest, so again, if we kind of use our example of like, okay, there's a box on the floor, maybe. So there we go. There's a box on the floor. And we were looking at the forces acting on this box. We've studied different specific forces already, and we've talked about, say, gravity. The gravity force might be going down and the normal force going up. And they're going to cancel each other out, which makes it the net force balanced. So if the net force is balanced, the net force is zero and there's no change in motion. So if it was at rest, it's going to stay at rest because there's no net force to change the motion. Same idea as if it was moving. So let's say I pushed this box and it was already moving. So make the like motion cartoon lines where like, oh, that's like, so let's say this thing is moving to the right. It's got some velocity. Notice that velocity vector that I just drew in with that arrow here is not the forces acting on it. It's just like that's the velocity of the object. So if this thing's already moving to the right and there's no friction to slow it down, there's nothing pushing on it to make it go faster, we just have our gravity and normal force, it will still keep moving and it'll just keep moving at a constant rate. So this is the same idea that's described in the second part. So if an object that is moving will continue to move in a straight line with a constant speed, if and only if the net force acting on it is zero. So again, our forces are balanced and the motion doesn't change. Newton's first law also implies that if it's not balanced, if the net force is not zero, then the motion will change. So it kind of, the antithesis of this idea applies to everything too. So if this is unbalanced, so let's say we did have some forces and we had a force going to the right, I'll make that, I don't know, some pushing force maybe going to the right. And let's say we had a friction force, which is a different color. I'll make it green and go to the left. And they are not balanced. So like you can see the red arrow is bigger than the green arrow. So if they're not balanced, it's unbalanced, and because the red arrow is bigger than the green one, and it's going to accelerate. And when it accelerates, it changes its motion. So it's not going to stay at rest and it's not going to be moving at a constant. So if it is accelerating in any way, speeding up, slowing down, turning, those are the three ways that are three kind of results of acceleration. It would be accelerating, and that is also implied by Newton's first law, even though it's not stated, it's implied. So it's known as the law of inertia, and inertia, the definition of inertia is just the tendency of a body to resist any change in its motion. So whatever it's doing, it just wants to keep doing. So if it's at rest, it wants to stay at rest. And if it's moving, it wants to keep moving. So that's what inertia is. The more inertia something has, the more mass it has. Because mass is the measure of inertia. So in chemistry class, you said it was the amount of matter in an object. In physics, we call it the amount of inertia, and that's measured in kilograms. So we've talked about mass when we did the gravity concept as well. All right, so that's the first law. It's just kind of governing how things change motion. Oops, wrong. The next one is Newton's second law. And Newton's second law has a really long sentence, and it says the acceleration of an object is directly proportional to the force applied and indirectly proportional to the mass. You don't really need to know all that. It's just like it's an equation. So this is essentially the equation you would be using, which says that the net force acting on an object is equal to m times a, m being the mass, a being the acceleration. So that's how you'll see it in most textbooks. This symbol, that's the Greek letter sigma, and that f sigma means just add up. So that's the net force. It's a different way, mathematical way to write it. So that is like the way you'll see it in textbooks a lot of times, or if you go Googling Newton's second law, that's probably what will come up, F equals ma or some sort of that. The way that makes a little bit more sense is if you actually solve it for acceleration. So the acceleration is equal to the net force divided by the mass, and that makes more sense, right? So let's talk about the acceleration of an object. So if you want something to accelerate more, you can change these two factors. So if you wanted to increase the force on an object, so if this mass was constant and I applied a bigger and bigger force, what would happen to the acceleration? It would get larger. So this would be increasing. That'd be an increase in the acceleration because this value is directly related to A. The other way that you can look at it in this concept is that mass is indirectly related to acceleration. So if the net force was constant, so if applying the same amount of force, but I apply it to a more massive object, so if you apply it to a heavier and heavier object, your acceleration is going to get less. So that is that concept. So those are kind of the relationships. This also gets us our unit of what a Newton is. So a Newton is a kilogram meter per second squared. And because it's a force, it's a vector quantity, so it has a direction. This is just doing a couple basic problems with net force and mass and acceleration. So if we had, going through these quickly, a 3 kilogram object, so that's the mass, and an acceleration of 4 meters per second squared going east, that would get us an answer of 3 times 4. So it would basically be F equals ma, or the net force. So I'll do it that way to make it a little bit better. So net force equals mass times acceleration. So that would be 3 times 4. And again, you can do that in your head. That'll get you 12, 21, 12 newtons, and that would be going east. So it's just a multiplication kind of problem there. The next problem says if we pushed a 30 kilogram object, so if we think about this, our mass got bigger. If we pushed it with the same amount of force, so we're pushing it with 12 newtons of force to a 30 kilogram object, what would happen to the acceleration? So we said that if mass gets bigger with the same force, our acceleration should get less. So we would expect our acceleration to get less. We can use the same kind of relationship and just plug in the numbers. So shrink this a little bit. That much. So Fnet equals ma again. If I plug in, it would be 12 as my force. My mass is 30, and then I'm looking for A. This time I'm solving for acceleration, so I would divide 12 by 30. And that's going to get us 0.4. So instead of being 4, it's going to be 0.4. That would be meters per second squared. And that would still be going east because our force was directed east. So we said our acceleration up here was 4. Our acceleration here is 0.4. That makes sense because we are applying the same force to a mass that is 10 times bigger. So if it's 10 times bigger, the acceleration would be 10 times less. We're dividing by a factor of 10. So that is that one. And then finally, the third law is something you've probably heard of. It's called an action-reaction pair. So it's like for every object, there's an equal and opposite. For every action, there's an equal and opposite reaction. You maybe heard that before. That's like the short version of it. It's not exactly like very descriptive of what's happening, but it says whenever one object exerts a force on a second object, the second object exerts an equal force in the opposite direction on the first. So I'm going to use a couple pictures again. So if that is our box, and let's say we apply it to a different, we'll have them touching. I have two boxes. One is maybe bigger than the other, so that you would assume that they're maybe different masses. So the bigger box on the right, and the smaller box on the left, they're pushing against each other. So let's say this box is pushing to the right. Oops. Instead of a line. And we'll give it a color. So we have a force from, if we call, there we go. So we'll call that object 1 on object 2. So object 1 is pushing on object 2. And what we're saying, whenever one object exerts a force on a second object, the second object is going to exert an equal force. So they're going to have a force that is the same as this one. So if I try to grab that arrow and clone it, there we go. It's going to exert the same amount of force, 1 on 2 as 2 on 1, except we're going to have to flip it over. So it's going to go the opposite way. So there would be an interaction between those two arrows. So the one arrow is going to the right, the other one is going to the left, and they are equal in size and opposite in direction. Okay, so this is not cause and effect. It's not one thing applies a force to the other and then the second waits a second and then does the next one. They happen at the same time. So if you imagine like you were gonna go up and push the wall, if you start touching the wall, you can feel there's a force pushing back on you. So you're applying a force on the wall is applying a force back on you. So that's what this third law is all about. And again, they're equal and opposite in size. So this would be like the force of 1 on 2, and this would, the arrow going back to the left would be the force of 2 on 1. So the way to get the third law always correct, and I'm going to ask you guys to kind of identify an action reaction pair in a couple different situations. You want to make sure that you show kind of the idea. So it says identify the two objects that are interacting. So this is the object 1 would be one object, and object 2 would be a second, or I used A and B, so let me try to be consistent. So we'll call this one A. So that's A, and we'll call this one B. Fix that real quick. There's B. So A pushes on B and B pushes back on A. So the action, it doesn't matter which one you put first, but I'm going to underline the nouns. So object A, that's one noun. Object B is a second noun. And then you always have a verb. So the verb is always pushing or pulling depending on what's happening. So I'm just saying they're pushing on each other. So object A pushes on object B to the right. And then object B would push back on object A to the left. So that's how you set it up. It's sort of like caveman talk is how I describe it sometimes. So object A push object B right, and then object B push object A left. You will always have the same verb. So it's always pushes, or if you use pull in your first sentence, it'll always be pulls for both of them. The direction switch, it could be up, down, left, right, whatever, north, south, east, west, whatever directions you have. And then it's just changing the order of the noun. So object A and object B, and the first, if that's your action, the reaction just switches. Okay, so they just trade the orders. So that is it. You will always get them right if you follow that statement. Okay, so that's just a summary of Newton's laws. I'm going to stop there and pick up the next video. Oh, let me get through one or two examples of this. So if I push down on a book, so this is the book, and that's my hand. It's not a very good hand, but you get the idea. So my hand pushes down on the book. So hand, I'm just going to use H for hand. Push. And I'll use B for book. So this is B for book. My hand push book, and I'll use the arrow. You would write down. The reaction to this would be what? So the reaction would be the book pushes up. So again, to get them, you just trade these. It's just switch and flip. So you trade the order, and you flip the arrow. So this would be the book push. You could write I because that's what I used in this sentence. So book push Mr. Pepper or Bill or I, or if I just said hand, that's fine. I'll use hand in this one. So we'll make this an H. Hand push, book down, book push, hand up. And that is an action reaction pair. That's all you have to do. Another one, I'll skip the earth one. My hand pushes the water backward. So again, if we're imagining somebody swimming. Okay, so there's my hand. And I'll make that direction backward. And we'll make this stuff some water in here. So there's the water. My hand, so W for water, H for hand. So hand push water back. The reaction to that would be the water pushes or push the hand. And if backward was the original direction, it would be forward. For the reactions direction. So the water pushes on the hand with the same amount of force going the opposite way. All right. So that is it. That's all you have to do with those. And that's how they work. Okay. Next one we're going to get into is lesson 5.3 vector review and steps in solving force problems. So we'll work out how to do that. So be well, have a great day, and I will talk to you in the next video.